So now we want to calculate how do we get exactly 95% of the values? How do we get exact 95% confidence and avoid that empirical rule that uses rounded values? So what we want to get to is this idea of if we have our curve, how do we grab exactly 95% of the values in the middle? Whereas the empirical rule only gave us about 95%. So that value of 2 in that empirical rule was describing 2 standard deviations above, 2 standard deviations below, which that 2 is actually a z-score in that it's describing how many standard deviations away from the mean, and that's exactly what z-scores are. And it's just that if you use a z-score of 2, it's not quite right to get exactly 95%. So what we want to do is find the correct z-score. What z-score actually works there to get 95% in the middle? So finding z-scores, that's where we need to go to the standard normal curve. That standard normal curve is our curve of z-scores. And remember, this curve always has a mean of 0, standard deviation of 1. So what we want to do is, using that standard normal curve and centered at 0 and moving some standard deviations above, some standard deviations below, we want to trap 95% of values in the middle of this distribution. So what we would do is use technology to find that z-score right there, that specific z-score that traps 95% of the values. This value right over here on the left would be the same. This would just be negative, this would be positive. But in general, we're just going to grab the positive value out of ease. Using technology, finding this, you might need the tails, which if you have 95% in the middle, that means we'll have 2.5% above and 2.5% below there. So once you have all of this, this is just using your technology with a normal curve, given a certain area under the curve, finding that cutoff point. So you could do is find using this mean and standard deviation, where is the area above this 0.025? And what technology should give you is a z-score of 1.96. So as you can see, this is very close to 2, but this is more accurate. So using the empirical rule, just to get an idea of the formula we were using, what we did is we started with our sample proportion, and then with these intervals, you're starting at that middle. You always want to move above and below. So as we saw when we used the empirical rule, it's that we added and subtracted the same thing. So instead of having 2 separate calculations, we're going to do one big one, meaning in the middle here, where we have 2 separate ways of looking at the subtraction, looking at the addition, for simplicity, we just combine it with plus or minus. This tells us eventually it will split into 2 different forms, as though we're adding and subtracting the same thing over here, which when we were using the empirical rule, that number 2 came through to represent 2 standard deviations above, 2 standard deviations below, and it was multiplied by the standard error. So this right here, this is the formula we technically use. We had our sample proportion, that 0.4499. We added or subtracted. We used that distance of 2 to get to that idea of about 95%. And then we had our value for standard error. So now what we want to do is improve on this. Where that works for the empirical rule, we want to improve this and get away from using the empirical rule. So this is the exact way that we should have done this, and how we want to do this for future problems. You want to take your sample proportion, we're going to add or subtract, and since we want these 95% of values, this idea of 95% confidence, instead of using 2, we actually want to use 1.96. that's going to improve a more exact confidence interval there. This is a better z-score than that value of 2, and then multiply that by our standard error. So the only thing that changes to make it more exact from the empirical rule is this special z-score. It makes it more accurate for capturing the correct percentage in between the two values. So let's calculate the exact outcome. So our p-hat value, that was the 0.4499, and then plus or minus, and that we're going to have that 1.96. And for standard error, I'm going to go ahead and copy the original calculation, just because it's best to put everything from this right side of the equation into the calculator at once to avoid any rounding errors. So what I'd want to do is think about this as two separate pieces of an equation. This left-hand side is done. That stays the same. And then we're going to add or subtract. And what would be nice is just to simplify to a single number over here. So what I would do is type in all of this into the calculator, and then from there get a single value, which should be a 0.0189. And this will be a nice setup for just having a simple calculation, because then we split into our two scenarios, the one where we subtract between those values, and then the one where we add between the two values. And this is going to give us our lower bound and our upper bound. So lower bound comes from the subtraction, and that would be a 0.431. Upper bound comes from the addition of the two values, which should be a 0.4688. So now the idea is, if we make our sentence, these are more accurate values. So we can say exactly we are 95% confident that, and then using these percentages, 43.1% to 46.88% of all HR professionals use social networking sites to research their job applicants. What's changed is now we don't have to round this, we don't have to say about 95%, we are exactly 95%. And we have our improved range that has the exact values, and then we continue on describing the population. That's what we'll go over in the next video, is how do we make these sentences to make sure they contain everything that we need. But before we go to that, this is our general form for our confidence intervals of proportions. You're taking some sample proportion, or you can also describe this as the point estimate. So taking that point estimate, we always add or subtract, and then what goes over here is called the margin of error. So the margin of error is the combination of multiplying this special z-score times, this is our formula for standard error here. So this form is similar to what we drew up here, it just makes it more vague, because what we can do is change our confidence level. We did a 95% confidence level here. What we could do is change this to 99%. We could become more confident. When we do that, it changes the z-score that we need to use. So that's our piece there. That z star can also be called a critical z-score, and it's denoted by this z star. And it's coming from the confidence level, and that using our standard normal curve, if we're at that curve and we have some percent confidence that we need, what we want to do is trap that percent confidence in the middle, and our z star value would be this value on the right hand side. Again, you could find that left-hand value, but it would just be negative. So this positive z-score, that's what's going to go right there. And that'll be in another video where how do we find our z-score based on different confidence levels. So from subtraction, you'll get the lower bound, and from addition, you'll get the upper bound. Before doing this, your first step before calculating is you should always check conditions first. Always go through those condition checks, because especially using the z-score, it depends on the bell-shaped curve. In order to use that normal curve, We need to make sure we have large enough samples. And then our last piece, just to describe margin of error, it's the multiplication of those two. And this often gets mixed up. So this piece alone with the square root PQ over N, that's our standard error. So just that piece is our standard error. As soon as you multiply it by Z star, then it becomes margin of error. So just be careful of what's being asked for because they sound similar, margin of error, standard error, and the difference is this multiplication of Z star. Margin of error has the Z star, standard error does not. All right, in the next video we'll talk about writing our sentence conclusion.